So let me just recap what that was about. So what's the name game? You have several piles of matches. So I think I said 3, 5, 7, right? Some. So what you are given is a vector of numbers, each denoting a pile of matches. Right? There are two players, 1 and 2, who will take turns, and of course one starts. That's why she's called 1. And what are the moves? Pick a row, pick a heap, take k greater than 0 matches from it. Of course, there should be k matches, right? You can't remove what is not there, right? And the winning condition, the player who wins last who moves last wins. That is, if it's your turn and there is no match for you to pick, you lose. Okay. So this is the standard condition. There is also the so-called Mézières convention. The Mézières convention is simply the opposite. Right? Doesn't matter. So most of these games have these. So this is a classic example of a two-player zero-sum perfect information game. And might as well throw these terminologies around. Two-player, zero-sum, win-lose, perfect information game. As opposed to other games which are not these, right? Meaning, for instance, of course we'll look at multiplayer games. Zero-sum, these two are there and don't confuse the two. Win-lose games means that there is a definite winning condition, right? It's not always the case that both can lose or both can win. All these possibilities are also there. So zero-sum means that if I win, you lose. That's it. And perfect information game means all moves are public. The board is in front of you. What I move, you see, etc. etc. There is no asymmetry in information. And of course, this is only an idealization, but it's already a lot of fun. Okay, so this is the name game. And what is the notion of a strategy? A map from a strategy for a player, say for player 1, sigma, a map from player 1 positions to that player's moves. Yeah, this is the basic idea. Strategy is an advice that tells you if you are in this position, make this move. It's a function, deterministic in this sense, tells you what to do. And we also said that if I have now two strategies, sigma for player 1 and sigma tau for player 2, this fixes a unique play. Right? Because you start at the initial position, somebody's turn to move, player 1's turn to move, sigma will say what to do, make a move. Now it's player 2's position, this thing, tau will tell him what to do. Keep on doing and you get a unique play. And if the play ends, which it should in a game like NIM, it will result in a loss or a win for one of the players, right? Exactly one of the players. Right? So now you say sigma is a winning strategy for player 1. If for every tau of 2, sigma tau is a win for 1. Right? Sigma is a winning strategy if you look at every possible strategy that player 2 could be using. If you look at the play resulting in it, it's guaranteed to be a win for player 1. So the question that you ask is, so and you say that a game is determined, if from every position, every game position, either of the two players has a winning strategy. Right. So, and if so, is this idea clear? So this talks about, so from this position, player 1 may have a strategy. From another position, player 2 may have a strategy. From a position, neither of them may have a strategy. A determined game doesn't have the third possibility. That's what we are saying, right? And so, of course, one natural question is, given any game, G, now we are only talking about games of this kind, is it determined? This is a question that you can ask. If you have a finite presentation for a game somehow given to you, it's an algorithmic question immediately to ask, is it determined? Can I find out?
What do you mean by finite game? Finite number of states or?
Finite description of the game. You didn't look at me. I'm only talking about finite games anyway, but I'm right now. But I'm saying given a finite description of the game, that's what you need, right? What do you mean given any game? It has to be given as an input to you, right? I should just write down the move somehow for you, right? That's possible. We'll see how we can present games a little later. But this is a natural question, is my, right? I hope you admit it's natural. There is a tense silence here. So, okay. So what about NIM? Is it determined? Right? Then the next question you can ask, suppose it is determined. Suppose you have a yes to this. Then the next question, determine the winning regions. Well, actually, why should I have a yes to this? Even otherwise I can ask. That is, take the positions, take all the positions and partition it and say, this is all the wins, these are all the positions from which player 1 has a winning strategy. These are all the positions from which player 2 has a winning strategy, and this will be, if it's a determined game, this will be empty, that's all, right? So this is the notion of winning regions, which is extremely interesting and important. I would like to characterize that. Now, this is not, as stated, is not quite a clear algorithmic question, because the set of positions may in general be infinite. You may need to look at it. The NIM game, as we have talked about, notice that the set of positions is finite. From any given initial configuration, if I give you an initial configuration, right, what are the possible positions that this can lead to? Yes? Suppose this is the heap this is the configuration that I give you. You have to pick one of the heaps, remove some. You keep doing it, how many possible configurations that you can get to? You can calculate the number, but it's certainly a finite set, right? And therefore, I could ask you a question of this kind. In general, it's not clear, because positions can be in such a way that you get into loops. Of course, then you learn. But then you know that even if you have loops, there may be like a finite graph presentation of it. You can do something, right? We'll get to graphs. Of course, that's always much more fun. And then you can ask this kind of questions. Determine the winning regions. Then, of course, the next question is, given a position, who wins from that position? Now, does the question make sense? What does it say? If I give you a particular position, like for instance this one, right? From this position, who is it that won? Determinacy will only say one of them has a strategy, the other one says who. Now, when I write something like this, there is a classic ambiguity here, right? And this ambiguity is very inherent and important in game theory. And what is that? What do I mean by who wins? You can only say who has a winning strategy, right? Now, there is an assumption. This comes in various ways. Let me just put it here. Let me just say perfect players. I mean, come on. What if I have a winning strategy but I don't use it, right? What if I play stupidly? It's my birthright as a human being to be stupid, right? Right. So all that you brush aside, right? Think that when I say who wins, all we are saying is which of the players has a winning strategy. Now, and that's very important, because the space of strategies in general could be very complicated. How do you select a particular strategy? right? And that could be, so you could be hiding an enormous amount of detail in this. But the mathematical question that we are talking about when I write something like this is only who has a winning strategy. And of course, the more looser question is, can we compute that strategy? Compute such a winning strategy. So so that has to do with the fact that if the strategy space is rich, right? This poor player, you can't stop saying that there is a winning strategy. But if you're, for instance, a finite state automaton, how would you compute it? If you're a Turing machine, polynomial time Turing machine, can you actually play in such a way that you win, right? So in my understanding, I would say solving a game means answering these questions. At least these questions. There can be more questions of interest to ask. Like yesterday I was talking about things like stability kind of notions and all are of interest. But at least one should. So then you can say you're solving a game completely, right? So in that spirit, how about the NIM game, right? Now for the NIM game, now how many people have already solved a game? Okay. How did you do it, or did you find it somewhere? If you found it somewhere and repeating it, then you can wait. If you have thought of a strategy yourself, I would like to hear it.
No, 2 heaps I solved it.
No problem. For 3 or for n heaps?
For n I solved it.
Okay. So I'll hear you. Somebody else?
Sir, actually for a single heap there was some problem, like you can take 2 or 1 stones and all that. For that I found a strategy, but in general I saw it in the net.
Saw it in the net. Then you can wait. Yeah. No, I have no problem with it. One should read and find out. But all I'm saying is then give the others a chance to think about it. That's all. So if you have come up with a strategy yourself, I would like to hear it. No, you found it somewhere on a book or something. Yeah, that's fine. No problem. Anybody else? Because others should have a chance to try and discover the strategies, no? So, yeah. So let's take the case of 2 heaps, right? So yesterday, as soon as I said it, somebody said for 2 heaps it's trivial, blah, blah, blah. I want to. Somebody had this idea. Huh? He's not here, huh? Who said this? No, who is not here?
He's not.
Oh, okay, fine. So then you can remind me of what he said.
He didn't say, but I mean equal, if starting equal then.
Okay. So let's see. This is and that is the point, in fact. So suppose there are 2 heaps. So I can get rid of the general GAN, right? Look at NIM. So there are 2 heaps, M and N sitting in front of you. Now, what kind of strategies would the 2 players use? Player 1 has to move, right? You are the oracle advising player 1. What would you say? What should player 1 do? Let me say this. Little tick, yeah? What would you advise player 1 to do? In fact, what would you advise player 2 to do? That seems more obvious to me. What is the symmetry in the game here? The 2 heaps are of equal size. So what player 1 has to pick one of the 2 heaps. Now one of the 2 heaps doesn't matter because both are, this is what I need to use. Okay. Now if supposing you are player 1, you make a move. As player 2, now I know that you have picked 1 heap. And I have got an identical heap in front of me. So what does that suggest? Any move you make, I can make in the other move, other heap. Not the same move in the other heap. Yeah. So this is what is called copycat. Right. For instance, suppose you remove the whole of 1 heap. You would be stupid to do it because what would I do? Copycat, I'll remove the entire other heap and then you are finished. Okay. Suppose you pick only 1 stick from the first heap. What will I do? I'll pick 1 stick from the other heap. Right? So I'll simply do copycat. And is it easy to see that copycat strategy is winning for 2? Is it clear? I mean, I'm not going through elaborate this thing, but it should be straightforward to see, right? So it's clear that if the two heaps are equal, copycat strategy is there. So player 2 has a winning strategy. But if they are unequal, that's not obvious to me. Copycat strategy may not work, but maybe there is some other strategy for player 2. So don't be in such a hurry, right? If the heaps are unequal, if for instance it's m and m plus 1, right? Player 1 removes the entire first heap. If the player 2 follows copycat, doesn't help, right? Okay. So what should, in this case, what are the options?
I will remove n minus, the player 1 should remove n minus m sticks to make it equal, and then I will follow the
Wonderful. This is what I was. Thanks. Right? See, you reduce it to something that you know, no? Right? I know that when it's two games, when the two heaps are equal, it's losing for player 1. So what will I do? I'll make them equal and give it to you. I know that it's losing for you, therefore it's winning for me. See? You need some argument. That's what I'm looking for. So player 1 reduces it to mm, which is losing for 2. Therefore, one has a winning strategy when. So for 2 players, we have completely solved the game. I mean, for 2 heaps, right? If there are only 2 heaps, is it clear that we have completely solved the game? We have looked at the initial configuration. We have partitioned the winning regions comfortably, saying look at whether the heap sizes are equal. If they are equal, it's player 2's region here. All unequal ones here. This is empty. So that answers everything that we have. It's completely trivial. So what about 3? 3 heaps. I think we now know enough about NEM2.